Welcome back to MATA35. We don't actually have that much more time for this lecture, but luckily this is a relatively short one. So let's go ahead and talk about how we can use power series or Taylor series to approximate functions. So how do we approximate sine of x? There are many different ways of approximating sine of x. You could draw out triangles because sine is, of course, the opposite over the hypotenuse. But if you're a calculator or a computer, you might want other ways of quickly approximating a value. So one way of doing this is the sine function. Now, modern calculators actually use something more complicated called the Quadratic function, a Quadratic algorithm. But one way of approximating sine of a value is by using the Taylor series. So let's try approximating sine of 0.5 radians by hand. How do we do this? So sine of 0.5, you can plug this in actually into the you can plug this in, and what you get is you get 0.5 minus 0.5 cubed over 3 factorial plus 0.5 to the 5th power over 5 factorial minus 0.7 to the 0.5 to the 7th power over 7 factorial, and so on. Yes, so when there's a question about radians versus degrees. Yes, so when we're dealing with these power series, this is always in radians. So basically, radians are the more natural way of thinking about. So degrees are an arbitrary measurement construction. Radians are the natural mathematical way of thinking about angles. Yeah, so these are all in radians. So what is this equal to? This is equal to 0.5 minus 0.125 divided by 3 factorial, which is 6, plus 0.03125 over 120 minus ... So let's just take the first two terms. That's 0.5. This is approximately equal to 0.5 minus 0.02083, and so on. And so this is approximately equal to 0.47916. And what is the actual value? The actual value of sine of 0.5 is equal to 0.4794255. So you notice that even though we only took the first two terms of the Taylor expansion, we were able to approximate it by cutting off the rest of the terms, and this allows us to very quickly approximate what sine is equal to. The sine of 0.5 is approximately equal to 0.479, and the error is, of course, in all these other terms that we got rid of. But you notice that these other terms, well, they're divided by some big factorial, and there's some small number divided by some big factorial. And so these terms give you very little error. And now, if you were actually worried about this in practice, you would also prove the amount of the remainder using Taylor's remainder theorem, but we're not going to worry about this for the purposes of this class. And so the crux of it is, we can often approximate a function by just cutting off its Taylor series after some number of terms. This is something that the physicists do really, really often because, well, oftentimes if you're a physicist, you don't really care about having too many significant digits because your measurement's going to have some error anyway. And so you can often do these approximations as a physicist or engineer with just a few of the Taylor series terms. So let's try it out. What is e to the 0.5 approximated using the first three terms of the Maclaurin series? So let me remind you, e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on. And I'm asking you to approximate it using the first three terms here. Oh, hopefully I didn't make a math error. Let me see. So, okay, so we have a couple of different replies. We have a C and an E. Well, let's actually try computing it. So what's e to the 0.5? E to the 0.5. Oh, okay. It looks like most of the votes are in for C. Okay, good. So e to the 0.5, that's approximately equal to 1 plus 0.5 plus 0.5 squared over 2 factorial. 2 factorial is just 2 times 1. Oh, wait a moment. I made a mistake. Yeah. Okay, well, 2 factorial. Which is equal to 1. Okay, so that's 1.5 plus 1 over 8, which is equal to 1.5 plus 0.125, which is equal to 1.625. Which is none of these. So the answer is actually E because I made a mistake in computation. Yeah, so the answer is actually none of the above. Yeah, because it is actually 1.625. So the answer was E here, and I made an error in my original computation. What I did is I accidentally divided by 4 instead of divided by 2, which would give C. But importantly, e to the 0.5 is actually equal to 1.6487. So this approximation is actually pretty close, even though we've only taken 3 terms. So this is none of the above. Okay, and so this brings us to, where did the factorial go? Oh, 2 factorial is equal to 2 times 1, which is equal to 2. Okay, so this brings us to different types of approximations. So, if we just keep the first term of a Taylor series, we get a constant approximation. So let's give an example of that. This isn't necessarily a very good approximation, but f of x is equal to sine x plus cosine x. If you take the Taylor series, f of 0 is plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus f triple prime, etc. I'm not going to write them all out because that would take me infinite time. And we know that sine x plus cosine x is equal to 1, which is and so sine x, f of x is equal to sine x plus cosine x. So that implies that f of 0 is equal to 1 around 0. What does that look like? This is the graph of the function. I always forget the 1. Factorial always equals 1. Oh, what is the factorial equal to? 5 factorial is equal to 5 times 4 times 3 times 2 times 1. And importantly, 0 factorial is equal to 1. 1 factorial is equal to 1. 2 factorial is equal to 2 times 1, and so on. Okay, so what does this equal to? So what we're saying is that we have a approximation function, which is our approximation is just that's equal to 1. Because around the point 0, it's equal to 1. Now, this isn't necessarily this isn't a great approximation, but this is an approximation. And if you're close enough to 0, well, the approximation is pretty close. But this isn't great. So usually, whenever you're doing these kinds of approximations, you don't just take the very first term. So this was just taking the very first term here. Well, that's a constant approximation. We don't use these very often since they're not very good. But once you get to a linear approximation where you keep the first 2 terms, things get a lot better. So if we use that same function again, so f of x is equal to sine x plus cosine x. F prime of x is equal to cosine x minus sine x. So f of 0 is equal to 1, and f prime of 0 is equal to 1. So the Taylor series, f of x is approximately equal to 1 plus x. And when we draw this out, what you end up getting is I need to actually be able to draw a straight line. So that line actually corresponds to left lying here. So that is 1 plus x. And so you see your approximation is getting better as you add more terms. If we keep on going, we can get a quadratic approximation if we keep the first 3 terms. And so in this particular case, we have f of x is equal to sine x plus cosine x. F prime of x is equal to cosine x minus sine x. F double prime of x is equal to minus sine x minus cosine x. So f of 0 is equal to 1. F prime of 0 is equal to 1. F double prime of 0 is equal to minus 1. So then f of x is approximately equal to 1 plus x minus x squared over 2. So this is just taking more and more terms of the Taylor series. And it turns out when you draw this out, you end up getting something like, which isn't exactly your function, but it's getting closer and closer as we add more terms. So, and importantly, often the qualitative facts we're interested in can be captured by linear or quadratic approximation. So a constant approximation isn't necessarily that great. You might have some function like this, and at some point, let's say here, a constant approximation is just the straight line. Whereas a linear approximation at that point would tell you if is the function increasing or decreasing. So that would be this line here, which is a better approximation because that's the tangent line, right? And the quadratic approximation is the function concave up or concave down. So in this particular case, your quadratic approximation might look something like this. So as you add more and more Taylor series terms, your approximation gets closer and closer to your original function. And importantly, we can do this for both single variable and multivariable functions. So a function f of x has a linear approximation at a of f of a plus f prime of a times x minus a. So here you have some constant, and here you have the slope, right? So you can approximate a function by its value at that point and its slope, and this is just the tangent line. A multivariable function has a linear approximation as well, but what you need is a constant, and you need the slope in x direction and slope in y direction. And so you can also get a linear approximation of a multivariable function, and that looks something more like this. So you notice that what we have here is you have a tangent plane. So you have a constant approximation here. So we have f of 1, 0 is equal to 1. So the constant approximation is just the horizontal plane. But a better linear approximation is this tangent plane. So this plane here is the linear approximation. And it turns out that the f of xy is going to be equal to 1 plus 2 times x minus 1 plus 0 times y is equal to minus 1 plus 2x. I am not going to expect you to be able to do linear approximations. This part of the lecture is just trying to give you intuition for linearization. And so you'll note also that this here, the slope df dx of 1, 0 is equal to 2 in that direction, and the slope del f del y at 1, 0 is equal to 0 in the y direction. Okay, so basically you can take linear approximations even of multivariable functions. And you can do this even with multivariable functions that then map to something that's also multidimensional. So remember, we just said that a multivariable function f of xy has this linear approximation based on its partial derivatives. So what you can say is that f of xy is approximately equal to f of ab, the value at this point, the constant approximation, times, and I've rewritten this as a gradient and a vector. So going back to our linear algebra stuff, we can rewrite this as a gradient and a vector. And then if you have some other function h that goes from r squared to r squared, from the plane to the plane, that's two functions f of xy and g of xy, then the entire, you can approximate, give a linear approximation of the h function by taking the Jacobian matrix. So this is the Jacobian matrix multiplied by some vector. And this gives you a linear approximation of these functions that are really hard to draw because they go from R2 to R2. So they're directions in the plane. And this brings us to nonlinear phase portraits. So remember, h of xy is approximately equal to this constant plus the Jacobian times some vector. And this approximation holds locally around every point and therefore around each equilibrium. And that means you can approximate the behavior by looking at the Jacobian matrices eigenvalues. And that brings us to these sorts of these local phase portraits where you look at each of these equilibrium values and then you look at the linearization, so the Jacobian around each of those equilibrium values, which tells you the behavior around each of those points. And this is why we're able to, we don't have to do linear approximations, right? Because you're kind of confused about it. The only linear approximations I am going to ask you to do is taking the Jacobian for these phase portraits. So basically, a large part of today's lecture was trying to explain all these other techniques that we taught you, but didn't really explain why they work. So last week, I remember I talked to you about taking these Jacobians and looking at the eigenvalues to find the local phase portraits. Why does that work? It's because of these linearizations and power series expansions. So you only have to do linear approximations insofar as you need to be able to use the Jacobian to understand the behavior of a phase portrait. And I think that's actually where I'll end today. So I'll end a little bit early. I'm around for office hours if you all have any questions.